Hi, in this video we're going to look at parametric equations. So before we do that, let me give you just an example of what they are and where it might be used. This drawing represents what would happen if an object was propelled into the air at a 45-degree angle at 48 feet per second. The graph can be modeled by this equation. So at any given time, for any given value of x, I will know how far in a linear direction that ball has traveled and how high it is based on this equation. But there's one variable that I can't involve, and that's time. So what if I wanted to know how high it was after 10 seconds or 3 seconds, or how far away the ball was from its initial launching after 10 seconds or 30 seconds. In order to do that, I need to enter in another variable, and oftentimes we call it t, and that's called the parameter. So in our case here, if I take this rectangular coordinate, Cartesian coordinate equation, if I write it in terms of t, I would say x equals 24 times the square root of 2t, and y equals negative 16t squared plus 24 radical 2t. These are called parametric equations. If f and g are continuous functions of t on the interval I, the set of ordered pairs f at t and f at g is a plane curve. So what happens is, instead of writing a function of x, so I've got f at x equals something, I take x and write it as a function of t, and I take y and write it as a function of t. Those are parametric equations that will give me some kind of a plane curve, where t is called the parameter. So let's take a look at an example. Alright, here I have two parametric equations, x equals 2t and y equals t squared plus 1, and we're going to consider that on the interval of negative 2 to 5. The square brackets means we're going to include negative 2 and we're going to include 5. Now, this right here is talking about the values that t is going to take on, not the values that x and y are going to take on. So, what we're going to need to do is make a table. So notice that I've got the t column with the values from negative 2 to 5. For each of those t values, I'm going to put it in here and calculate x, and put it in here and calculate y. So I get this kind of a table. So when you go to graph it, you're going to graph your xy points just like you would on a regular graph. Now if I graph those points and connect them, because I needed to use all the values from negative 2 to 5 for t, notice that I put some arrowheads on here because that is what the graph path is going to follow. Over here, this is where t equals negative 2. As t increases, my path follows this route, and up here is where t equals 5. So not only do you get a curve, but you get orientation depending on the values of t and what happens to x and y as t moves through the values from negative 2 to 5. Okay, let's take a look at what it looks like when we do these on our calculator. The first thing you need to do is press the mode button and then go down and highlight PAR for parametric. Then do second quit to get out of there. Now we're going to go to our y equals screen, and notice now that it has x equals and y equals in terms of t. So here's our equation, x equals 2, and push my variable button and it puts a t in there. Okay, let's go down for the y. Y equals t squared, so I push my variable button and my squared, and then plus 1. Alright, now I need to go to my window and see what it looks like. Notice that it has a t min and a t max. Well, we wanted to have our minimum, our t, go from -2, and then we wanted it to go up to 5. And the smaller the step you make, the more accurate it's going to be. Instead of plotting t equals these integers, let's set it for 0.1. And then you shouldn't have to mess with the rest of it. As long as you've set your t values, you should be okay. So if I push graph, there's the exact same curve that we had before. Now if you want to see what's happening on that, push trace. And notice that as I go from the left, that's where t equals -2, you'll see the t values are going to be increasing slowly. As they do, you can see the xy point. So if I just hold this down and keep pressing it, you can see the orientation as t gets larger. Okay, here's another example. This time it's a trig parametric equation that we're going to be graphing. So I would recommend that you go to your zoom and go down and just hit zoom trig, because if you do that, your window is going to be already set up. Your t's will go from 0 to 2 pi, and I like this 0.1. You could make it even smaller if you wanted, but we're told to have our t's go from 0 to 2 pi. So now I need to go to my y equals screen, enter in x equals 4 sine 2 theta. So hit your variable button. It's going to be a t because we're in parametric mode. And then I'm going to have y equals 4 cosine theta. And let's see what it looks like. Did you notice? Did you see how if I trace this, if you watch the cursor as it goes around, it does quadrant 1, then it goes over to quadrant 3, and then quadrant 4, and then up through quadrant 2. That's how far it travels from 0 to 2 pi. Okay, let's look at another one. Alright, here's another example. Here's another pair of parametric equations with trig. So I'm going to go and just make sure I'm in zoom trig. Alright, I'm going to go put my equations in. I've got x equals cosine of 4 theta and y equals sine theta. Let's see what that one looks like. Well, that's interesting. Let's zoom in on that a little bit. I'm going to do a Z box. So I'm going to just kind of go over here to this corner, hit enter, and then I'm going to make my box. And hit enter again. Let's see what that looks like. Interesting. Okay, let's push our trace button. Here's t equals 0. Now if I push my right button, t is increasing, and look what happens. When t gets to be, it looks like about 1.4 or 1.5, it turns around and it comes back this way. T continues to increase. About 4.7, it comes back, and at 2 pi, which is about 6.2 or 6.28, I end up where I started. So it's often interesting to see the orientation or the path that your graph follows as you change the values of t. Now, if we want to eliminate the parameter, let's say I've got parametric equations and I want to eliminate the parameter t. Well, if I want to do that, I'm going to solve one of the two parametric equations for t and then substitute into the other one. So let's look at an example. I've got two parametric equations. I need to solve one of them for t. Because this has a t squared, this looks like it would be easier. So if I multiply both sides by 1/2, I get 1/2 x equals t. Or in other words, t equals 1/2 x. So take this and substitute it in for t right there. So I end up with y equals 1/2 x, quantity squared because it was t squared, plus 1. So I get y equals 1/4 x squared plus 1. So this will give me the exact same graph that I had before, but without the parameter of t. Alright, this one looks a little more challenging. I need to take one of these equations and solve it for t. This one looks a little bit better, so I'll go with that one. So in the process, first thing I'm going to do is I'm going to multiply both sides by t plus 1 in order to get the t out of the denominator. So that gives me tx plus x because I'm multiplying through by x. On the right side, all I have is a 1. Now I'm solving for t, so I've got tx. I'm going to subtract x on this side, on both sides, so it shows up on the right. Then I'm going to divide by x on both sides, and it looks like I've got t equals 1 minus x over x. So that means over here, every place I see a t, I need to substitute this stuff. So let's take a look at what that looks like. Wow, take a look at this. When I substitute the 1 minus x over x in for the t here, and here, and here, and here, that's pretty messy. If I do FOIL on this, and then multiply through by 3, I get this quantity. When I multiply this through by 6, I get this quantity. Now, this is still pretty messy. So, the trick that we have in dealing with complex fractions is to take a look at all of your denominators. X squared, these have a denominator of 1. So if you look at all of your denominators, the LCM is x squared. So we're going to multiply, if you think of this as the entire numerator, and this is the entire denominator, I'm going to multiply by x squared over x squared. Let's see what that looks like. When I multiply by x squared over x squared, that's the same as multiplying through every single term on the top and the bottom, numerator and denominator. So what happens here is this x squared cancels this one cancels one of these, and I just have an x left. This one cancels one of these, and I just have an x left, and this one cancels this one. So now all of my denominators are gone, so I'm just going to look at what I have for the numerators. So when I get the numerators all written down and the denominator, this all cleans up to something that's really pretty simple. I get y equals x squared plus 3. That would be quite easy to graph. So sometimes it's nice to take the parametric equations and be able to write them without the parameters. Now we're going to go the other way. We're going to take an equation that is just in x and y, and we're going to introduce a parameter. Now we're going to go the other way. We will either be given what t equals in terms of x, or we can make up our own. So in this example, we're told to find a set of parametric equations for y equals x squared plus 1 if I'm given t equals x. Now remember, parametric equations are going to be x equals something and y equals something. Well, if you're told that t equals x, that means x equals t. So the x component is finished. Now, if y equals x squared plus 1 and x equals t, we're going to take that x out and we're going to put a t. So y equals t squared plus 1, and there we have our parametric equations. Let's look at a different parameter. Okay, let's look at one more example. This is the exact same equation that we had before, but I'm going to change the parameter. So instead of t equals x, I've got t equals x plus 2. Well, let's remember our parametric equations are going to be x equals something and y equals something. So if I come over here, I can subtract 2 from both sides and get t minus 2 equals x. So that means x equals t minus 2, and I'm half done. Alright, so now, since x equals t minus 2, where I see an x in my equation, I'm going to substitute t minus 2. So for this guy, I'm going to substitute for the x, and I'm going to put t minus 2, quantity squared, plus 1. When I square that binomial, I get t squared minus 4t plus 4, and then I have a plus 1. So I end up with y equals t squared minus 4t plus 5. So my final equation over here, I've got x equals t minus 2, and I've got y equals t squared minus 4t plus 5. Now, because this had the exact same equation for both of the examples that I just did, that means the graph of these parametric equations is going to be identical to the graph of the previous parametric equations. If you change the parameter, you will change the parametric equations, but the graph will continue to be the same. So in this section we've talked about what parametric equations are. We looked at some examples of how the orientation works if you trace it on your calculator when it's graphed. We eliminated the parameter so that we just had an equation with y and x, and then we also went the other way. We introduced a parameter. So you should be able to go both ways. Alright, that'll do it.